So I made the decision to start this new chapter just by doing notes and homework because I think it's fairly easy, it's fairly basic probability stuff. And given that my time is limited with you all, I will try to save a day by doing it this way rather than giving you a spiral over the weekend. So, very basic. You have a spinner, there's 5 parts, all the same size, so you're equally as likely to land on a 1 as on a 3 as on a 5. So, this basic probability that you've done before is what's your probability of spinning a 3? Well, the outcome of 3 happens only one time, and the number of possibilities was 5. So there's a 1/5 chance we spin a 3. Okay, probability of a prime number. Okay, you have to know what a prime number is. A prime number is something that has exactly 2 factors. 1 has only 1 factor, 1. 2 has 2 factors, 2 times 1. 3 has 2 factors, 3 times 1. 4 has 3 factors, 1 and 4 and 2. And 5 has only 2 factors, 1 and 5. So of those 5 outcomes, so that'll give you your denominator, number of total possibilities, the ones that satisfy being prime are 2, 3, and 5. So 3 of the 5 outcomes satisfy being prime, which means you have 3/5 chance of rolling or spinning a prime number. Okay? A 1 or a 5. Again here, the total number of outcomes is still 5. How many of those would satisfy being a 1 or a 5? 2 of them. Okay? 2/5. Something else we're also going to learn, and this is a good takeaway, or in probability means addition. So you could technically find the probability of spinning a 1 and add it to the probability of spinning a 5, and sometimes there's an overlap. Sometimes there'd be something that's double counted. It doesn't happen in this particular instance, but you have to subtract away the probability of both things happening. Meaning, if there was something on here that was both a 1 and a 5, which is weird to talk about because that would never happen, but we may see it come up in a second. It would be double counted as in your chances of getting a 1 and your chances of getting a 5. So you would want to subtract it off one time so that it wasn't double counted. But your probability of rolling a 1 is 1/5. Your probability of spinning a 5 is also 1 out of 5. And the probability that both of these things happen, that on any given spin, because you're only spinning it one time. So on that one spin, what's the chances of you spinning both a 1 and a 5? Well, there's no chance that would happen, so that would be 0 out of 5. So that's just 2/5. Now, if you did it that way, but it's also easy to wrap your head around doing it the initial way. But here's a situation, and I'm going to do this the addition way. I'm going to look at the probability of even plus the probability of prime. Now, the even numbers are 2 and 4, so that's 2 out of 5. Plus, the prime numbers that we talked about were 2, 3, and 5, so there's 3 out of 5. But we double counted one of them. We double counted 2 as being something that's even, because it is, and being prime, because it is. But in reality, we don't have if I added these the way it is right now, I'd have a 5 out of 5 chance of getting an even or prime, which is a 100% chance, which isn't true. I don't have a 100% chance of spinning an even or a prime, because if I spun a 1, that would not make me a winner. That would not be an even or a prime. So there's got to be a chance of this not happening. It's not going to be 5 out of 5. But the reason that happened with the 5 out of 5 is because we double counted the 2. So this is where we subtract the probability of both. So what numbers on there are even and prime? This one, 1 out of 5 of them. So we have to subtract off that 1 that we had double counted. And now we see that we have a 4/5 chance, really, of spinning an even or a prime. If we didn't do it this way, we just looked at it, is this even or prime? No. Is this even or prime? Yes, it's even and prime. So Is this even or prime? Yes, it's prime. Is this even or prime? Yes, it's even. You answer yes if it's one or the other, and this one is prime. So you can see the 4 out of the 5 satisfy being that. So keep that in mind. In probability, or means addition, but you always have to be careful of knowing that you have to subtract off anything that fell into both categories that you might have double counted. All right, now this is a different situation. Here we were only spinning the spinner once, and sometimes we had multiple options of what would make us a winner, quote unquote. This one, we're spinning the spinner twice, and let's make this a competition. Suppose you're told that you would win if you spun a 1 and a 3. Okay? If you spin a 1 and a 3 in your 2 spins, okay, because you're spinning twice here, that would make you a winner. So, and in probability is like multiplication. And here you don't really have to, you don't at all have to worry about double counting anything, because these are 2 totally separate spins. So on the first one, what's the probability of spinning a 1? And on the second one, what's the probability of spinning a 3? So your probability of spinning a 1 is 1/5. Probability of spinning a 3 is also 1/5. And so the more events you stack on top of each other, the more stipulations you have. Like, you're a winner if you spin a 3. Okay, that's pretty easy to do, 1/5. If you have to spin a 1 first on your first spin and also spin a 3 on your second spin, your chances are going to go down, because you're creating more stipulations, things that have to happen in an exact certain way in order to become a winner. And that's what happens when you multiply by fractions. When you multiply by fractions, your number and your chances get smaller. Now your chances, because we have to make 2 things work out perfectly, your chances of being a winner are only 1 in 25. Okay? On B, the probability that your first spin is an even and the probability that your second spin is a 4. So your probability of spinning an even, there are 2 out of 5 of these that are even, times your probability of spinning a 4, that's 1 out of 5. So you get 2 out of 25. That's your chances of that happening. So when you start stacking on multiple scenarios and you use the word and, multiplication really drops your chances. Okay? Just some basic vocab. An experiment. Your experiment is spinning the spinner. A possible outcome, spinning a 3. An example of an event. The event might be, again, spinning a 3. Or, like, the outcome is that you actually were spinning a 3. The event might be the event you're looking for. You're looking for the, like, what is the probability of spinning a 3. I don't really love I'll say spinning an even would be an example of an event. Outcome is a specific outcome. We got a 3. Event can be a little bit more generic. What is the sample space? So the sample space is what could come up. So if you spin 1 time, the sample space is the list of outcomes. So if you're only spinning once, you could spin a 1, a 2, a 3, a 4, or a 5. That's your sample space. It's typically written in curly brackets. The other experiment was spinning twice, and that has a much different sample space, because you could spin a 1 and a 1. You could spin a 1 and a 2. Don't read that as 11. Read that as 1 and 1. Maybe I'll do this. I'll do 1, 1 with a semicolon. 1, 2 with a semicolon. You could spin a 1 and a 3. You could spin a 1 and then a 4. So your outcomes for spinning twice, if your experiment is spinning twice, then your outcomes are like a 1 and a 1, that's your outcome. Or maybe you spun a 1 and a 3, that's your outcome. And this would be a pretty long process to write these all out. because once we get through the 1s, we then have to go into the 2s. A 2 and a 1. A 2 and then a 2. A 2 and then a 3. So that's a very long list. You'd really have to be very clear about that. Sometimes what people do to help them better organize that is they create a tree diagram, which you probably will remember once I show you. So your first event would be the top tier. So right away, you're spinning a 1, a 2, a 3, a 4, or a 5. This is your first event, meaning your first spin. Those are your possible outcomes on that first event. And then your next tier of the tree would be your second event, or second outcome, or from your second spin. Okay? If you spun a 1 the first time, your possible second outcomes are still 1, 2, 3, 4, and 5. If you spun a 2 the first time, second time you again might spin a 1, 2, 3, 4, and 5. And so each of these would have still 5 branches on them. So the total number of items in this list, if we were to keep going, would be 5 times 5, because there's 5 branches under each of those 5. So there's 25 different outcomes in this list. Very different than the number of outcomes if you're only spinning once. If you're spinning once, you have 5 outcomes. If you're spinning twice, there's 25 possible outcomes. Okay? Switching gears a little bit, minimum probability, 0, which would equate to 0%. They ask for probability, you have to give 0, but sometimes it's easier to conceptually think of it as a 0% chance. The maximum probability is 1, which is a 100% chance, if you want to think about it conceptually that way. Okay? 2 definitions that you might have to call on, or you might see these words theoretical or empirical. This might also say experimental probability. Okay, the easiest way for me, experimental, to give you a concrete example of how this would be different would be flipping a coin. Let's say you flip a coin 10 times. Let's say you get tails, heads, tails, 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 heads. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Theoretically, the probability of getting tails, this is what theoretically the probability should be. We expect it to be 1/2, right? This is in theory. We've got 1 tail out of 2 total possible outcomes, those outcomes being heads or tails. Empirically, though, this is the probability based on what we actually saw happen. Out of the 10 trials, how many were tails? 1, 2, 3, 4, 5, 6, 7. So in theory, the probability of tails should be 1/2. Empirically or experimentally, what we actually saw, these were based on the observed results, it was actually 7 out of 10. Now, in theory, the more trials you do, if this is a fair coin, if you did 1,000,000 trials, it should get closer and closer to 1/2 as you do more and more trials. But, weird things can happen. It's all luck of the draw. All right. A coin is flipped 3 times and the result is noted each time. So you have 3 events. We're going to do a tree diagram. So event 1 is flip 1, and your outcomes are heads, tails. Then your next layer of the tree is flip 2. So if you got heads the first time, your second flip could still lead to a heads or it might lead to a tails. If you got tails the first time, your second flip, again, could be a heads or could be a tails. And then flip 3, if you already got a heads and a heads, you might get a head again, or you might get a tails. If you got a heads and a tails, still you might get a heads or you might get a tails. And each of these still has branches coming off of them. These are 3 different events. And they really are completely independent of each other. whether or not you got a heads or a tails on the first one has no bearing on whether or not you get a heads or a tails on the second one. I mean, you'd like to think over time, again, it would balance out, but really these are independent events. What I'm about to flip my third time has nothing to do with what I flipped the second or first time. So there's the tree diagram. The sample space would be any kind of avenue. So if kind of you follow this maze going backwards, this would be heads, heads, heads. If you follow this maze going backwards, this one would be heads, heads, tails. So heads, 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 tail. If you follow this final outcome backwards, that would be HTH. Here's a final branch, so follow that chain of events backwards, HTT. And you would just go on and so forth. So just under this main, I'm done with this left side, there were 4 of those. And there are 4 more of those that I would do THH. This one would be THT. This one would be TTH. And this one would be tails, tails, tails. So you continue to list all those out. Okay? I guess I'm going to do that because I have, do that quickly. THH, THT, TTH, TTT. The tree diagram really helps so you don't miss anything. Okay. Now, that's of the whole total experiment, which is flipping 3 times, there are 8 possible outcomes. So out of those 8, how many are all heads? Only one of them, the first one, 1 out of 8. How many out of the 8 are exactly 2 heads? Well, this one, this one, this one, 3 of them. Exactly 2 heads. And then how many are all heads or all tails? So again with that word or, we want to look at the probability that they're all heads plus the probability that they're all tails minus the probability that they're both all tails and all heads, which is impossible. So that'll definitely be a 0. But the probability of all being heads is 1 out of 8 plus the probability of all being tails is 1 out of 8. The probability that is any of these outcomes all heads and all tails? No. So that's 0 out of 8. So you just get 2 out of 8, which is 1/4. And you could go through your list since we have it, and you could circle anything that's all heads or all tails, and it would show you 2 out of 8 of them fit that bill. Okay. Exercise 4 gives us a survey, some survey results. So which sodas were preferred by a blind taste test? So soda A was preferred by 18 people, B was preferred by 24, C was preferred by 11. There were 53 people total surveyed. Okay. Find the empirical, so that means based on the evidence, that a person selected at random from this group, so out of the 53, what's the chances that they would prefer soda B? 24 out of 53. Express your answer as a fraction and as a decimal accurate to 2 decimal places. So there's your probability of a fraction. 24 divided by 53 to 2 decimal places would tell you 0.45. And again, that probability is always between 0 and 1. Find the empirical probability, again, based on this, that a person selected at random from this group would not prefer soda A. So not preferring soda A means they're preferring probability of preferring B or C. Hope that makes sense to you. If you don't prefer A, then we're looking at the probability that you actually prefer B or C instead. So that would be the probability of B plus the probability of C, minus the probability of anyone preferring both, which I don't think is allowed, so that's probably going to be 0. Probability of B is 24 over 53, plus the probability of a C is 11 over 53, and then no one can prefer both, so that's not allowed. So we get 24, 34, 35 over 53 as a fraction, and as a decimal, 0.66. Again, that's between 0 and 1. Okay? Another way to do this, if it's not A, you could actually calculate A. The probability of preferring A is 18 out of 53, which would be 0.34. So if your probability of, and I'll think about this in percentages for a second, if your probability of preferring A is 34%, then the exact opposite of that, the probability of not, and I'll use that symbol as not, of not preferring A, these two probabilities have to add up to 100%, because it's either one or the other. It's either A or not A. And that's what we will call complements, you'll see. So if it's A, it's 34%. So on the flip side, if it's not A, that has to give you the rest of the percentage up to 100%, or the rest of the probability up to 1. And so it kind of works out that way. It's like if someone says the chances of it raining tomorrow are 30%, then the chances of it not raining have to be 70%. Because you have to be one or the other. That's called being complementary events in probability. They would then have to add up to 1. It's kind of like complementary in geometry, angles having to add up to a certain thing if they're complementary. Same thing here. If we have complementary events in probability, it's just that 90 degrees is not the target. The probability total of 1 is the target. Okay, and on our last exercise here, we're considering an experiment where we first toss a coin and then roll a 6-sided die. Okay, so if I'm going to quickly wrap my head around what's going on here. My first event is tossing a coin, so I'm going to get tails or heads. Once I get a tails, pretending, I'm then rolling a 6-sided die, which means I'm going to roll a 1, 2, 3, 4, 5, or 6. If I get a heads first and then roll a die, again, I'm going to get 1, 2, 3, 4, 5, 6. So if I were to start listing those, my possible outcomes, my sample space would be T1, that's a tails with a 1, tails with a 2, tails with a 3, so on and so forth. Once I get through my tails, I'll do heads with a 1, heads with a 2, so on and so forth until I end with heads with a 6. So that's two initial branches, each of which have 6 off of them. 2 times 6, there's 12 items total in my list. 12 different outcomes of this kind of multi-tiered experiment. Write a set of ordered pairs such as, okay, that's pretty much what I was doing. So I already did that. We'll call this part A. I did leave some ... dots, but I think you can fill in the blank through T6 and fill in the blank H3, H4, H5, which I skipped with ... Now write a set of ordered pairs that represents the event of getting a tail and an even number. So a tail and an even number, that's really just tails 2, tails 4, tails 6. Tails 2, tails 4, and tails 6. I guess it just maybe only wanted a set, so I could have just done tails 2. Okay, this is going to be called set A. This down here is being called sample space set S. And here's where, okay, finally they're going to talk about complement, which I kind of already did. The complement of a set A will be all of the other ones. So A's complement is anything that we didn't include here. So T1, 3, and 5, and then all of your H's will be the complement of A. So write out the complement set of A. So complement of A is going to be the T1, 3, and 5, and then all of your H's. So if there were 12 items total, 3 in set A, that means there's 9 in the complement. 1, 2, 3, 4, 5, 6, 7, 8, 9, just to make sure I didn't miss any. And we're calling this set B. So the probability of A happening, meaning a tails with an even, is 3 out of 12. And separately, the probability of B happening is 9 out of 12. And you'll see, again, that those two complementary events should add up to 1. They do. 12 out of 12 is 1. So, kind of a variety of stuff, but hopefully all of it's fairly simple and hopefully a review. And then you have your homework worksheet so that we can kind of hit the ground running to the new stuff, the stuff that kind of expands on probability basics on Monday.